Okay, so there's a few new folks here. So I was already planning on doing this. I'm gonna very briefly kind of summarize how we got to where we are. We're at part 3 now of well, go ahead.
Is camera all right?
That camera should be on. Did you move it?
No, but I mean, is it all right? I may have kicked it with my foot.
Oh,
It's supposed to be on the screen or you?
it's supposed to be, it's both. If anyone on Zoom is worried you're not getting a good view, go ahead and speak up and I'll adjust things. But for now, we'll carry on. So this is part 3 of a 5-part series on creation geology. And the first presentation, for those of you who are here, we talked a lot about the idea of uniformitarianism and this philosophy of geology. And we talked about the history of where these ideas came from. It's kind of an abstract thing for many of us, but it ends up being really important. And it lays the foundation for the story that we're going to be telling today about Mount St. Helens and why it was so significant. We talked about gentlemen like James Hutton, Charles Lyell, who really preceded Charles Darwin and anticipated him and laid a philosophy in geology that served as the philosophy that guided Charles Darwin. And I got some notifications just now. That same philosophy then guided Charles Darwin in his development of the theory of biological evolution. And the core motto of these men was the idea that the earth changed through slow and gradual processes. And not only that, but the processes that were at work in shaping the earth to make it look the way it does today are the same processes that operated in the past, and they're the same processes that will operate in the future. So we have consistency of processes in geology. And in addition to that, they also argued that these processes always worked at the presently observed rates. So we see today that soil erodes in a rainstorm a little bit every year, and we can extrapolate that back and come up with an idea of how long it would take a mountain to be eroded, for example, or a hillside to form. And so they argued that rather than looking at the earth as sort of a frozen snapshot with a violent and a catastrophic history, which was the commonly held belief before these men, they advocated that we should instead see the earth as a system that is constantly evolving slowly, and that the processes that are operating on that are the same processes, as we said previously, that worked in the past, and that they'll always work that way in the future. Stephen Jay Gould, we quoted him a number of times in that presentation last December. He very cuttingly points out and critiques these men, even though he is an evolutionist, because he said that their theories were not driven by evidence. They didn't go out into the rocks and see something that made them realize that the earth changed slowly over long periods of time. Rather, they had various religious and ideological reasons for wanting to believe that the earth and that reality worked a certain way. And they went out to the rocks and they applied what they wanted to see to the geologic data, to the evidence, and they came up with their theory. And so Stephen Jay Gould, in this quote, speaking of James Hutton, says that he imposed this idea on the earth. And Gould goes on to criticize that quite extensively, again, even though he himself is an evolutionist. And so he talked about these ideas. And then last month, we talked about the geologic theory of plate tectonics. And we talked about gentlemen like Antonio Snyder, who is a Frenchman, French geographer, who was one of the first people to really publish the idea that the continents used to fit together like pieces of a puzzle. And then his ideas were largely ignored, in no small part because he theorized that the continents broke up during the flood of Noah's day. And that was not a popular idea at the time, but it was revived by Alfred Wegener, who is known as the father of plate tectonics. And the gist of this theory is that at one point the continents were together, that Africa and South America were closed up and that there was no ocean in between them. And that at some point the continents broke apart and separated into their present locations. And there's many lines of evidence, we went over a number of them, that demonstrate that something like this is certainly true. We find many branches of science, many lines of evidence that show that the continents really do have a shared history, that they used to be together. It's a complicated history, but it's there. And so we talked about the ideas of plates of the continents moving and of collisions and of the interactions that these pieces of the Earth's crust have. And when the pieces of the Earth's crust break apart, and they move around, they interact in really extraordinary ways. And in fact, whenever you see really extraordinary geology, whether it's the highest mountains in the world or the deepest ocean trenches, you will generally find that there is some sort of plate tectonic action going on. It's India crashing into Asia to produce the Himalayas. It's Arabia and Africa crashing into Europe to form the Alpine mountain belts. It's similar processes going on to form the Andes Mountains. And so plate tectonics is an incredibly powerful theory that explains major features of the Earth's geology. And more pertinent to what we're going to talk about today, as we now look at the story and the processes at Mount St. Helens, it gives us, plate tectonics explains why we have volcanoes where we do and why we have earthquakes in the places we do. And the most important part of that story is this process of plate subduction. So when we have places on the Earth where one piece of the Earth's crust is crashing into another one, sometimes they collide and they crumple and they shove mountains into the sky. Other times, especially when we're talking about an ocean plate, an ocean crust, it dives underneath continents. And when it does that, you have relatively cold rock going deeper and deeper into the Earth's internal structure, which is very hot, as hopefully we all understand. And that process is the primary, not the only, but the primary driver of the Earth's volcanoes. Because as that rock is forced down into the hot mantle, the semi-molten region beneath the crust, some of it melts. And as it melts, it's hot, it's more buoyant, it's light, and it wants to rise, and it finds its way through fissures and cracks in the Earth's crust, and it eventually breaks out onto the surface, and that's what we call a volcano. So we talked about a number of these processes, seafloor spreading, for example. And what I want to get at with all of this is when we talk about Mount St. Helens is directly connected to the idea of plate tectonics. In fact, we really can't explain Mount St. Helens without plate tectonics. So plate tectonics is a very powerful theory. And it's a global theory, which is very interesting to those of us who believe in a global flood, because we are interested in global theories. We're interested in things that might explain how the entire surface of the Earth works together. The problem, of course, is that plate tectonics, as we talked about last month, is way too slow. When we talk about continents crashing into each other and lifting mountains into the sky, we're talking about motions on the orders of centimeters in a year, and that's fast. So we're talking about very, very gradual processes, very gradual activity. And so we talked about the work of creation scientists such as Dr. John Baumgartner, who developed an alternative spin on plate tectonics called catastrophic plate tectonics. And what he discovered, and he was able to model this through supercomputer simulations, is that plate tectonics actually works better when you speed it up. It can explain more geology if you suppose that it happened much more quickly in the past than it does at present. This is just a few snapshots of his computer simulation. And without going through all of the details, I just want to remind you that for our discussion last time, that this is not a ad hoc, well, if you speed this up, it's convenient for me, please believe it. There's actually good evidence to believe that catastrophic plate tectonics is actually a more accurate version of the theory. We find evidence of the old ocean floor, the old Earth's crust that would have subducted and sank into the Earth's mantle. We can still find that material through various seismic methods. This is a fairly recent paper, and this is a illustration of what this stuff looks like. That is a pile of the old ocean floor that is now sitting deep inside in the interior of the Earth. And what's important about it is that blue color there, it sets to demonstrate the temperature gradient. That is cold material relative to the rest of the mantle. That only can happen if that material got to the bottom of the mantle of the Earth quickly and recently. If that happens slowly over the millions of years that plate tectonics is supposed to have taken, none of that should be there anymore. All of that should have been assimilated. It should all be at basically a uniform temperature, and that's not what we see. So catastrophic plate tectonics, we talked about in detail last time. Just want to remind you that that is the dominant geologic theory or tectonic theory that creationists hold to. Not all creationists accept it, but most do. And it is a very powerful theory. It's a productive theory. It's able to make predictions, and those predictions have in fact been validated. So all that to say, we're talking about plate subduction. This idea that the ocean floor is in places in the earth, it's sinking beneath the Earth's crust, and some portion of that is melting. And of course, when we have molten rock, we know that as lava. So lava is just the liquid form of rock that's at sufficiently high temperatures, rock will melt. And that's the kind of temperatures we're talking about when we speak of volcanism. Now, what's interesting is that not all volcanoes are alike. And in fact, if you just take mantle material that's really hot, glowing orange stuff and bring it up to the surface of the earth, you will never get Mount St. Helens. You will get a volcano, but you will not get a Mount St. Helens. You will not get a Mount Rainier. You will not get the traditional cone volcano that a lot of us just take it for granted that volcanoes look this way. You won't get that by simply raising molten material out of the interior of the earth. What happens? That stuff is too runny. You instead form the lava flows like you see at Hawaii that we just saw in that previous video clip. But those lava flows are so runny, they don't form mountains. Or the mountains they form are the Hawaiian shield type of volcano. You never will form a tall mountain with that sort of lava. The kind of lava you need to form a Mount St. Helens is a very special lava called andesite. Without getting into the particulars, andesite, because it forms in subduction zones where molten material is forming underneath the continent, as it rises up through the continent, it picks up elements of silica. And that silica causes the lava that comes out of these volcanoes to be much less runny. It's almost like dry toothpaste in consistency. And what that causes is it causes gas to be trapped in that lava. When you trap gas in lava, you create essentially a bomb. You create an explosive lava, which is why we don't see lava flows of andesite lava very often. You don't see major lava flows happening at mountains like Mount St. Helens or Mount Rainier. Instead, when they erupt, we see ash. We see explosive eruptions that produce massive ash columns. Now, for those of us who have been in creation circles for a while and have talked about the Ice Age, one of the common ideas among creationists is that the Ice Age could be the result of volcanism happening during the Genesis flood. The idea being that if you have massive quantities of ash and volcanic aerosols in the atmosphere, you could have a cooling effect. And we know this happens because even volcanoes in the modern era have done this. They can lower the Earth's temperature by blocking out some of the sun's heat. And so we believe that that's part of the process that led to the development of the Ice Age. But it turns out you need andesite volcanoes to do that. So these volcanoes are very important to the creation model. Without them, you don't get an Ice Age because volcanoes like you see in Hawaii don't produce massive columns of ash that have any sort of effect on the Earth's climate. And so these andesitic volcanoes, like the Andes Mountains, which you might guess that's where the name comes from. In fact, that's where we get the term andesite in South America. These are the kinds of volcanoes that form the quintessential conical stratovolcano, a volcano that is formed of multiple layers of ash, of mud flows, of pyroclastic flows, and other sorts of volcanic stuff that cascades down the sides of the mountain, and through many successive eruptions, you build up this volcanic cone. And that's the kind of volcano that we tend to be familiar with, in large part because North America has a whole lot of them. So all along the northwest, going up into Canada and all the way down to California, this is the eastern shoulder, if you will, of the Pacific Ring of Fire along the west coast of the United States. We have this chain of andesitic stratovolcanoes that we call the Cascades. The Cascade Volcanoes are some of the youngest volcanoes on the planet. Whether you're a creationist or an evolutionist, they happen very late in geologic history. They include volcanoes such as Crater Lake, which no longer possesses its cone. The mountain collapsed, but it is one of the Cascade volcanoes. Mount Hood is another very picturesque example of a stratovolcano in the Cascades. Mount Rainier, the tallest mountain in North America. And of course, Mount St. Helens, seen there as it looked before the 1980 eruption. So with that background, now you understand why Mount St. Helens, hopefully, is where it is and what it's doing there. It is a stratovolcano formed over a subduction zone where the Pacific ocean crust is diving under the west coast of North America. Some of it is melting, mixing, it's remelting continental minerals and crust, and it's erupting along this range and forming these volcanic peaks. Mount St. Helens was considered the most picturesque of the Cascades. The Cascades are very beautiful volcanoes. If you've been in the area, you know what I mean. They're extremely aesthetically pleasing. They're very symmetrical, and Mount St. Helens was probably the most symmetrical of them all. And so it had a real kind of mystique about it. People nicknamed it the Queen of the Cascades. It was a place where people would fish, people would hike, they'd climb. There was a whole network of lodges and cabins. And there was always this problem in people's minds going back to the 60s, 70s, 80s, as geologists were thinking more circumspectly maybe about the fact that this is a volcano. Maybe we should be taking this a little more seriously and not treating it as just a big recreation enterprise. But it had been dormant. It had been quiet for some time. Now, in reality, it had been active as recently as the 1800s, but that predates, the photography. It predates, the kinds of things that we use to keep the memory of volcanoes and major geologic events alive. And so it was kind of taken for granted that this was a stable element of the landscape, and people really didn't think too much about the possibility of certainly a violent eruption, maybe a puff of steam, maybe a little bit of volcanic gas being emitted, but generally speaking, this was not something people were very worried about. So when we talk about the eruptions in Mount St. Helens, one of the challenges is that people tend to remember, if they remember anything about it, they remember the big eruption on May 18th, 1980. But volcanoes, like pretty much anything in geology, they don't just happen once. There's always successive, usually somewhat smaller aftershocks or smaller eruptions that will happen. So there's actually a series of eruptions that take place over the 1980 to 1982 time span. And then Mount St. Helens, of course, erupted as recently as 2004, and even today still continues to put off some amount of volcanic venting and earthquakes. So we're going to take a look at the May 18th eruption in a little more detail, and then we'll talk more. We'll summarize the other eruptions that are important to our story here. So this is Mount St. Helens again. Was I on the wrong slide there? Did you all see this? Okay, good. Sorry, I wasn't sure if which slide was actually up on the screen there. So this is Mount St. Helens before 1980. 9,677 feet, not the tallest of the Cascades, but one of the tall ones. By the time you reach April of 1980, people knew something was going on. The mountain had been shaken by numerous relatively small earthquakes, and in the spring of 1980, there began to be actual eruptions, small eruptions. There was a small crater that opened on the top of the mountain. And geologists realized that this is something that needed to be watched very closely. And so they began to converge. Geologists from all over the nation began to converge at this spot, climbing the mountain, examining it, measuring it, doing things that would be considered very unsafe in retrospect. But no one knew what to expect. This could be all the activity that they saw, and then the mountain might go back to sleep. And so they were watching this very closely. The eruption, when it took place on May 18th, 1980, there was, depending on how you want to count it, there was a half dozen different things that happened essentially simultaneously. And so it's difficult sometimes for people to understand. In fact, when you go to Mount St. Helens, you go to the visitor center, you hear a presentation by a ranger, people very quickly get their head spinning because there's so many things that happen. And it's difficult to keep track of what happened first and at what point in the story are we in. And so what I've done here is I've broken up the eruption into 6 main points that I want to talk about in a little bit of detail on each one. Now, I put these into an order that is loosely chronological. However, you have to understand that other than maybe points number 1 and 2, everything here is happening simultaneously. And so don't worry about that. The order is not important to understanding the story. Just sit back, relax, enjoy the pictures. But keep that in mind that as we talk about steam blast or landslide or mud flows and so forth, this is all happening together, right? I can't tell you the story in a multi-stream concurrent manner. I have to break it out and tell it to you in an order that makes some sense. But the reason why I say this is because when you talk about the flood, and as creationists, we often hear people say there's no evidence for Noah's flood. There's no evidence for the flood. What are you talking about? There's just no evidence in geology for the flood. And usually our response is to stifle a laugh, because for most of us creationists, we feel like, what do you mean there's no evidence? The earth is scarred. There's abundant evidence for the flood. But when they say there's no evidence for the flood, especially when it's a geologist saying this, or somebody with some scientific training, what they usually are saying is that I know what floods look like. They leave a layer of mud, some trees. I see no flood layer that goes across the whole globe. So what are you talking about? In other words, they have a very simplistic view of what a flood is. And this is something that you have to watch out for when you start talking about catastrophes like Mount St. Helens, because they're not simple events. They involve many independent events and processes that are all happening together. And so when someone says there's no evidence for the flood, it's betraying a way of thinking. They have an extremely simplistic view of what the flood should do. When in reality, if the flood happened at all, and if it was a catastrophe on the scale that the Bible says it was, you can't just say, I don't see a flood layer. You have to understand that the flood would have involved hundreds of processes and events happening in a complicated, choreographed sequence that you can't reduce to just, I don't see a mud layer, therefore there's no flood. And so just like with Mount St. Helens, you can't go out into the area of Mount St. Helens and point at some hill and say, I don't see evidence for an eruption, because that formation you're looking at is just a slice of one part of one of these sequences that we're going to talk about here. And so you have to remember that the catastrophes by their nature are complicated events with many things going on simultaneously. And we need to give them a little more credit than they sometimes get, because especially when talking about the flood, people tend to really dumb things down. And as a result, they miss really important evidence. So that little soapbox moment aside, this is what got the geologists really worried and excited. Geologists, especially volcanologists, get worried and excited at the same time, because they're basically there looking for disaster, and they knew that the disaster was coming, because this bulge you see here, like a tumor growing on the side of the mountain, that is rock that's being displaced and pushed outwards away from the center of the mountain. Now, geologists and volcanologists understood what was happening there. They knew that, like any good volcano, there was a magma chamber beneath Mount St. Helens, and that magma, molten material, was rising, and that normally what should happen is it should make its way to the surface, open up a crater, and do an eruption. That's what Mount St. Helens has done hundreds, maybe even thousands of times in its history. But it didn't do that. That is not a healthy volcano, literally. And so what that told them was that something was blocking that magma, and that molten material was not able to get to the summit to erupt the way it was supposed to. What that means is that there's no release valve for that pressure. And so the only thing the mountain could do was expand in some way to make room for this material that was being forced into it. And they knew right away that that was going to fail. Now, that at the time, that's all they really knew. The geologists didn't know what mounts. They had never watched a volcano do this. And in fact, at that time, they didn't believe volcanoes did this at all. And so this set people, got people really worried, but they still weren't sure what kind of eruption they were looking at. They knew that that bulge would eventually give way, that there was going to be an avalanche, there was going to be a landslide. At some point, that mound of rock was going to be extended too far out and gravity was going to bring it to the bottom. And so geologists and the various government officials, they began to form zones where they were keeping people away from certain areas around the mountain. But there was a lot of pressure against doing that because people had property out there and they didn't want to be kept away from their cabin and so forth. And there were logging companies that had property in the area. Nonetheless, this set the stage for the fateful day, May 18th, 1980. I'm going to play a 1-minute video clip. And this is an excellent simulation slash, it takes actual photography from Mount St. Helens along with some additional animation and gives you a good sense of what took place on the morning of May 18th.
A magnitude 5.1 earthquake causes the north face of the mountain to collapse, triggering the largest landslide in recorded history. Pressure rising from deep within the volcano rips open the mountainside, toppling entire forests, scorching everything in its path.
So the very first event in our sequence is the landslide, that bulge. So eventually gravity was going to get its way, and that slab of the mountain was going to shake loose. And the earthquake on the morning of May 18th was the straw that broke the camel's back, as it were. And so as this section of the mountain slides down into the valley below on the north side of the mountain, what you're essentially doing is you're opening up the volcano. You're exposing the molten magma that is in the center of the cone to the atmosphere. And remember, we talked about we're talking about andesitic, dacite type of lava that is full of gas. And so it is very explosive. But beyond the magma itself, as the magma rose through the mountain, it was also accumulating water. Meltwater from the melting glaciers on the surface, on the top of the volcano, as well as water from beneath, from in the crust beneath the mountain. And that water was trapped in that same extremely high pressure situation to the point where it was superheated. It was above the boiling point, but it couldn't boil. And so the moment you take that overburden of that bulge off of that material full of superheated water, that created a steam explosion. And in fact, the first blast that you see in that video and in this picture here, the white clouds, that's not ash, that's steam. Now it's dirty steam. There's going to be plenty of particles and rocks and boulders and so forth, but that is the steam explosion. And that explosion behaved very differently than any volcanologist was expecting. That blast, that steam blast, moved at almost 700 miles an hour, pushing the speed of sound. It didn't break the sound barrier, but it was awfully close. And it did not explode vertically the way that all good volcanoes are supposed to do. It shot out northward horizontally across the landscape, and it outran the landslide. Notice that picture here. This is the side of the mountain, and in the next second, you can't see it. The blast has already outrun. The landslide is moving at maybe, what, 100 miles an hour, something around that. We're talking 700 miles an hour for this lateral blast. It quickly outpaces the landslide, and it flattens the forest. This is the most dramatic feature of the initial eruption, because again, the landslide, frankly, we don't know what it looked like. After that initial moment when it broke loose, the blast outpaces it and you can't see a thing. And unfortunately, we have to kind of look back and figure out what the landslide did in retrospect, because it's completely invisible to us. So the lateral blast, these three events here, the earthquake that triggers the landslide itself, which, as the video clip I mentioned, is the largest landslide. Well, it was the largest landslide in recorded history. Anyone remember a recent volcano going off somewhere? Very good. That is now believed to be the largest landslide in recorded history. It finally outranked Mount St. Helens. Of course, it was underwater, but nonetheless. And then the lateral blast. These three events happen essentially in a matter of seconds. And the thing I want to emphasize here, and as we go through all of these, is that we talked about gradualism, uniformitarianism, slow processes, slow rates. When we talk about Mount St. Helens, we have to think of extraordinary process and extraordinary rates. And that is going to be the key to understanding why this mountain did what it did and why it shocked so many people, because it showed that the surface of the earth and the geology of the earth can change and be reshaped through processes that are far beyond our everyday experience. Okay, so the next sequence we want to talk about, and it looks like I have a slight bug in my slides there because it's going to make me go through the whole, there we go, is what happened to that beautiful old growth forest that surrounded and the flanks of the mountain. Of course, it was completely devastated. This scene would, I've been back to this, I've been to this area. I know exactly where this is. Obviously, it doesn't look like this anymore. Many of these logs were in fact harvested, believe it or not, later on by the logging companies, because this is technically their property. They owned those trees and they wanted them back. But the damage to the forest was total. I mean, the trees were simply shredded, pulverized. As you get farther away from the blast zone, you move from areas where the trees were simply just exploded, there's no trace of them, to areas where they're flattened, they're toppled. That looks like, what, a field of grass. Those are old growth trees, completely stripped of their branches, needles, and so forth. And you're just looking at fallen stumps. Even today, you can still see remnants of the same devastation on the ridges that are directly north that bore the full brunt of that steam blast. Now, the landslide, we talked about that initially. It continued on its merry way, hidden by the blast, but continued its path nonetheless. You can see the scour marks there. There would have been topsoil, there would have been greenery, forest, and so forth, completely scraped clean by the landslide. I was out hiking there just last year. I thought that this rock here, it really caught my attention. Look at those grooves that are cut into that rock. Now, there's a little bit of controversy over what did those, but I'm pretty sure, and it's not just me, there's geologists that agree, that these grooves are cut by the landslide, by that side of the mountain that is just turned into rubble that is now flowing like a semi-solid slurry of boulders and broken rock flowing over the landscape and cutting, scouring, and grooving the bedrock underneath it. Now, directly in the path of that landslide, or not quite directly, but on the north face of the mountain, lies Spirit Lake. Spirit Lake is kind of it's a really interesting place because it's still there today, of course, but it's changed dramatically. It's not even looking at this picture, I don't even recognize it. Because the lake has completely changed in its characteristics. As the landslide material, we're looking kind of here from the north, orient myself here, kind of the northwest quadrant here of the mountain. Some of the landslide material came directly into the lake. And when it did that, it generated a tsunami. This is a simulation, not of Spirit Lake, but of Lake Tahoe in California, which had a very similar event. And you can see exactly what happened at Spirit Lake. Material from the landslide pours into one end of the lake, displacing the water and creating a tsunami that sends water 860 feet up the opposite bank. Again, completely scouring the forest. The logs that had already been shattered and toppled by the blast were now picked up by the tsunami and dragged, carried back into the lake, where they are to this day as Mount St. Helens or Spirit Lake's floating log mat. They believe that about 1 million logs ended up floating in this log mat, and about half of those logs remain there to this day. And the log mat is a fascinating feature all by itself, the way it behaves. It's not static. This is the log mat moves. It's pushed by the wind, and it has all kinds of really interesting characteristics. And I believe we'll talk about this in a future session. But the logs at Spirit Lake, as they absorbed water and as they began to sink, many of them, as you see in this photo, began to sink and float and then eventually sink in an upright position. And it was this observation, which happened in the mid 80s and late 1980s after the eruptions, that led even secular scientists to realize that they may have misread other instances of buried trees of so-called fossil forests, like this example here from Yellowstone National Park. They now realize that rather than these upright trees representing old forests that grew and were fossilized where they grew, but there's actually good reason to believe that they were also transported through a volcanic event, and that they are in a sense in a false growth position. We won't go into any detail on that, but just a teaser for a future discussion. So the aftermath of the landslide was a completely new landscape. And it's hard to really, even at the scale, it's difficult to really, put this into words. That mound, that valley floor there is about 200 feet higher than it used to be. A joke that we would hear or tell even when we would do tours out at Mount St. Helens is that you take people to a parking lot out to hike in this area, and you would ask them, so if you were here 1 year before the eruption on May 18, 1980, and you were standing right where you are now, what would happen to you? And usually they say, oh, you'd be killed by the explosion, by the eruption. And no, 1 year before the eruption, what would happen to you? It's a trick question. What would happen to you is you would be standing 200 feet in the sky, and you would fall to your death and probably get impaled on a tree, because that wasn't land a year before the eruption. And so that entire surface is brand new. And as time has gone on, and as plants and animals have repopulated the area, you can hike and you can picnic in this area, and it looks like a relatively established landscape. You can see some odd things about it, things like, trees that are upside down, that raises some questions. But nonetheless, it doesn't feel like a spot on the earth that was essentially behaving like a violent fluid. And yet that's exactly what it was. All of this rock, all of this material here was moving, it was flowing, it was acting more like water than as a solid. And it's essentially frozen, right? Because when the energy runs out, when the landslide loses the energy that keeps all that rock in motion, well, rock doesn't move. It locks together and it freezes, it stops. And now you have a relatively stable landscape, yet it was formed through a process that was anything but stable and anything but gradual. Again, extraordinary process and extraordinary rate. This lake, Coldwater Lake, did not exist before the eruption. This lake was formed when the landslide blocked off a creek, Coldwater Creek, and the water backed up into this newly formed basin. And this is a beautiful, pristine alpine lake. You can fish there, you can boat there, brand new. Well, now it's over 40 years old now, but as far as the landscape is concerned, it's extremely young. Notice that little island there in the middle of the lake. We zoom in on that a bit. That is a pile of material from the landslide. It's called a hummock. And that material came down from the mountain, across the valley, up a ridge, several hundred feet high, over the ridge, and into a basin, and is now sitting in the middle of this new alpine lake. Incredible reshaping and remodeling of the landscape that happened in a matter of seconds to minutes. So we talked about the Spirit Lake and the logs and the log mat and so forth. The next, yes.
Real quickly, a hummock, that's like a solid chunk of the mountain, right? That stayed intact, is it?
Good question. That's controversial.
Oh,
That was the people's first thought because, and I kind of skimmed over that, but I'll go back and talk about it a bit. This kind of landscape is called hummocks or hummock topography. These conical or triangular shaped hills and piles. So at one point when the dust was still settling, people's first thought was these are chunks of Mount St. Helens, these just slabs of rock. As they dug into them, they realized they weren't solid. And so it's been kind of a bit of a mystery. Remember, you couldn't see the landslide. Nobody knows what happened under that steam blast. I think there's good reason to believe that they never were solid, but rather they were, this is not the right analogy, but you know, if you mix up cake batter and you get clumps of flour, it's more of that kind of a phenomenon where it's pulverized rubble that through some sort of a hydrodynamic type process, it's not water, but it's behaving like a fluid. These sections stay together. They stick together for the ride. And when the landslide stops moving and everything else, all the dust settles, they stay standing they form these shapes. Yeah, there you go. Something like that. Again, that's not quite the right process, but it works as an analogy. But that was a thought. People did look at this at first and think that must be a solid rock. But when they got up to it, it wasn't solid. So the next character, if you will, in our story, our choreography here of Mount St. Helens is mud flows. And mud flows by far were the most damaging phenomenon that happened at Mount St. Helens and frankly at most volcanoes. Steam blasts and ash clouds and landslides, they're very devastating, but for the most part, they tend to affect a fairly localized area. Whereas mud flows can follow river channels, river beds and so forth, and cause much more far-reaching damage. And so the mud flows at Mount St. Helens caused the majority of the property damage from the eruption. They took out bridges, they took out roads. This is a fun little spot. It's kind of a bit of a touristy attraction on the road up to Mount St. Helens. That's an A-frame cabin, but what you can't see is that it's about a third of it is actually underground. That grassy lawn everyone's standing on is the top of the mud flow. So when the mud flows run their course, the mud flows are simply formed of its meltwater from the glaciers at the top of the mountain, mixing with ash and mixing with other volcanic sediment and creating this extremely erosive, gritty mud, which flows down these river valleys. And when it runs out of energy, when it stops moving, it just forms the new ground. And so again, you're talking about a surface that is now probably 20, 30 feet maybe higher than it was before the eruption. Maybe not quite 30 feet in this area, but in some places. And in this case, it swamped this A-frame cabin. The mud flows are believed to have caused about $1 billion of property damage by most estimates. Again, that's most of the damage was done through actually the destruction of property, stranding of shipping and so forth as these mud flows work their way through the river systems and into the Columbia River ultimately. The final element in the May 18th sequence is the actual eruption, right? So all these other processes that are going on, and we haven't even talked about the mountain actually erupting. And that definitely happened. Mount St. Helens erupted for 9 hours. This is referred to as a Plinian eruption, where there's a vertical ash column. So what's happening again is that molten material is coming up through the throat of the volcano. It's being exposed to atmospheric pressure, and it's exploding, and it's sending pulverized rock, which is volcanic ash, up into the sky. The ash column grew to a height of 12 miles, 63,000 feet. And it took only 10 minutes, by the way, to get there. And the total power of this eruption, of that magma coming up and exploding and erupting through the vent vertically, is estimated at over 400 million tons of TNT, which without doing all the math, it's about the equivalent of detonating the atomic bomb that was dropped on Hiroshima once every second for 9 hours. That's the energy equivalent of what was happening in the crater. And it's erupting vertically again, like good volcanoes are supposed to do. The ash cloud spread over a wide swath of the Pacific Northwest. It turned the daylight, at noon to essentially as dark as night. It fell like snow. It didn't cause quite as extensive of damage. It's that no one died from breathing in ash or anything like that. It was more of a disruption than anything else. And in a matter of weeks, the ash, it was caught up in the jet stream and actually made its way around the entire planet and came back to Washington, leading to a popular joke at the time: "Don't come to Washington. Washington is coming to you." So this is another map of the distribution of ash fallout from the May 18th eruption. And what I want to notice here is a focus there on the orange smaller circle there. That's where you had accumulation of up to 2 inches. Beyond that, you're talking about a light dusting, nothing really significant. Now, if you compare that ash fallout to other volcanoes in North America in history, Mount St. Helens quickly shrinks in size. It's not a large eruption by comparison to the eruptions that have happened on this continent, let alone elsewhere in the world in the past. In fact, what's fascinating is that about the ash fall from Mount St. Helens is that you can't find it. It didn't last that long. In a matter of years, it turns to clay, and you really don't have you don't find ash beds for the most part. If you do, when you do find an ash bed from Mount St. Helens, what you've actually found is a place where they shoveled the ash into a big pile, and it was thick enough that it actually has lasted this long. But there are other places from these much larger eruptions where we do find significant beds of ash, ashfall fossil beds in Nebraska. This is ash from a Yellowstone eruption, much more powerful and with much more ash output than Mount St. Helens. And we find beautiful ice age animals that are preserved in these ash layers. And so we see that the ashfall from ancient eruptions dwarfs by far anything that was done at Mount St. Helens. So that takes us through our May 18th, 1980 sequence. Of course, speaking of the cost of life from the eruption, it's actually surprisingly small. 57 people were killed on May 18th. Most of them were killed through the mud flows and through some of the other outbursts of material. No one, for the most part, there weren't many people in the steam blast area proper. Harry Truman was one who would have been an exception. He was one of the more famous people who made a show of refusing to evacuate his cabin. And everybody who died at Mount St. Helens was in a danger zone. They granted the geologists and the government folks, they didn't know how dangerous it was. And so they probably didn't enforce it to the degree that they would have in hindsight. But nonetheless, there was plenty of warning before the eruption on May 18th, even though there was also much uncertainty. The eruption, because it happened on a Sunday morning, May 18th was a Sunday, that also greatly minimized the number of people that were in harm's way. The following day, it's believed that there would have been hundreds of loggers in the area that was devastated by the blast. They would have been there in an attempt to harvest wood trees before they were destroyed. A few more statistics there. The mountain, of course, is entirely changed. The 9,677 foot summit is gone. It's replaced by this gaping horseshoe crater. And as we talked about previously, the landscape itself is completely remodeled. I didn't even mention this, but notice that there's Spirit Lake. And if you recall the earlier photo I showed where it was this fairly small basin, maybe a half to a third of the area it is now, because the lake bed has been filled up with avalanche deposit, landslide material. So the lake is now shallower, and it's actually riding much higher than it did before the eruption. So that is the eruption of May 18th. Now, there are two more eruptions we want to talk about here. pretty briefly that are important to the things that we see in the aftermath of all of this activity. The next one is from June 12th, 1980. And we're going to talk about something called pyroclastic flows. So this eruption was not nearly as powerful as May 18th, right? We talked about the ash plume, 63,000 feet high. Well, the ash plume from this eruption only reached 13,000 feet in elevation. And what would happen is that this magma would explode and material would be shot up into the air. And some of it would get caught up in the jet stream or caught up in the atmosphere, but much of it would come back down. And as it came back down, it would land in the bottom of the crater and then jet out the open horseshoe facing the north side of the mountain, and it produced what are called pyroclastic flows. Pyroclastic, the technical term, pyro referring to fire, volcanic gases, very hot, and clastic refers to clasts, which is broken pieces of rock. Pyroclastic flows are the most dangerous thing that a volcano does. I'll play, see if I can, oh, hopefully I can play that video clip to see if that doesn't want to go through. There we go. This is a wonderful video of a pyroclastic flow happening in close up, and it's amazing that they got this. Pyroclastic flows kill the most of the geologists and volcanologists that die at volcanoes. You would imagine these guys aren't going to get caught in a lava flow, right? They know better than that. They know where to stand and where it's going to be safe. The problem with pyroclastic flows is that they are almost entirely unpredictable. You just don't know where they're going to go. They can go uphill, they can go downhill. They're essentially behaving like a gas charged fluid. So they really do flow. They will follow contours in the landscape, and they will hit a ridge somewhere, and they'll be shot up into the air, and they'll come back down, and they can extend for miles until the energy that's powering them finally runs out. The folks in the video did get away, thankfully. But these pyroclastic flows are deadly. But they're also some of those interesting when it comes to the features that they leave behind, because the pyroclastic flows that happened on June 12th created these fine laminated, which refers to just thin, flat layers, laminated sediments or deposits. This is a photo taken by Dr. Steve Austin back in the 80s. This is a photo that actually my brother here, Solomon, took a few years ago. They're not quite as distinct as they were because of weathering and so forth, but these laminated pyroclastic deposits are really fascinating because what they have is they have many of the features that you see in fine strata in the geologic record. Here's another a photo that I took this last year while I was out hiking in the area. It can be difficult to see the laminations because the sediments at Mount St. Helens that were deposited, the conditions aren't really right to turn them into solid rock. For one thing, they're not underwater. They don't have the conditions that you really want to turn them into solid rock. They're partially indurated, as they would say, but they're not solid. I love this picture, and if you were into geology, you'll know why. But take a look at this. These strata, these layers, are actually curved. They're folded. And what's fascinating about this is that fold, obviously, there wasn't a point where the layers were flat and then they were moved in some way. And in this case, they're folded because there was some sort of an eddy going on inside of that pyroclastic flow, and it laid the layers down with this curvature. Now, these flat, thin layers are found all throughout the geologic record. This is an example of the Tapeats sandstone in Grand Canyon. The Tapeats sandstone also has some of these interesting fold features, including what we see here. This is of the Tapeats again, and then other sandstones, other sediments like the Coconino sandstone. We have these dramatic fold features, which also seem to be formed through some sort of a fluid process. And remember, the pyroclastic flows, even though technically they're not fluid, they behave like a fluid. They have a similar set of dynamics. Sandstones are roughly analogous. They're similar in composition to a pyroclastic flow. It's a different process, but we do see very similar things showing up. And what this illustrates is that it is not only possible, but it is actually a very it's actually very indicative when you see these kinds of features that there is a similar process going on, that we're looking at the evidence of a high energy, rapid event, and not a situation where you had individual layers of sand being put down in some ocean bottom and forming these sandstones in that way. So that was the June 12th eruption, Pyroclastic Flows. March 19, 1982, the last eruption we're going to look at. This eruption was the wimpiest of all the ones we're talking about, honestly. It really didn't do much at all as far as an ash cloud. It had been two snow seasons since the last period of volcanic activity. And what that meant is that snowpack and glaciers had started to build up again inside this newly formed crater. When the mountain erupted in March of 1982, while it didn't make a very impressive eruption, it did heat up the crater enough to melt that snowpack. And that created the final large mud flow in March of 1982. And I've got a video clip here of a mud flow, not the mud flow from Mount St. Helens, but a similar illustration. It probably does the whole way through. So a volcanic mud flow is also called a lahar, and that's just to distinguish it from any other sort of flow of mud. A lahar is a volcanic mud flow. It has volcanic sediments, and what makes them extremely powerful is that they tend to carry large boulders, large pieces of rock with them, and that makes them extremely erosive. They dig into the Earth's surface, they dig into the bedrock that they're flowing over. And so the mud flows in 1982, in their aftermath, in a matter of hours, they left behind what we like to call the Little Grand Canyon at Mount St. Helens. This is, again, a photo from Steve Austin from back in the mid-'80s. Here's a photo of what it looks like today. This canyon is in places well over 100 feet deep. It's not necessarily, you don't get like the vertical walls that we attribute like in Grand Canyon. And that's largely, again, because the material isn't solid enough. It's soft enough that it does erode and cascade down the side. And of course, it doesn't help when people like us show up and we climb up the sides and ruin the canyon. Sorry. But I have a panorama photo here. I'm going to see if this will play through, because it's difficult to really get the scale. I mean, that cliff there is, again, well over 100 feet tall, more like 140 feet. And this channel has formed the new river system, the new drainage valley for the north side of Mount St. Helens. There's a river flowing through this canyon. Before the canyon was here, there was no river. In fact, the old river, the Toutle River, had been buried. There was nowhere for water to drain off the north flank of the mountain. And it actually became a bit of a concern for the geohazard scientists working in the area, because they knew if there's no established place for water to flow away from the mountain, you could create a very unstable situation. So with the mud flow in 1982, there is now a fully formed branching drainage canyon, and the Toutle River now flows through this channel. Another picture up looking up the cliffs of the canyon there. This is again another view, a picture from just this past year. Now, what's fascinating and significant about this type of canyon is that it illustrates the power of sediment-rich water to quickly dig in and create and establish drainage systems and canyons in a very short amount of time. And we actually have a less impressive example of this not too far from home. Some of you may remember the Sock Reservoir, which gave way back in 2005. And there wasn't enough water really to form a full canyon, but nonetheless, you can see it was starting. You can see that gash there, and from the satellite photo here, you can see a longer view of it. As the water is pouring through it, it's digging into rocks, which is what water does. It erodes, but then it carries that rock with it, and that the rock being carried along, just like with the mud flow we saw earlier, increases the ability of the water to erode even further. And so it's almost a runaway effect, where the more it erodes, the more it erodes, and you can actually start to create canyon systems very quickly. And of course, this raises very interesting questions when we look at some of the even larger canyons that we see on the surface of the earth today, such as the Grand Canyon. And in fact, and I'm not going to go into any more detail on this because it's a topic for a future presentation, but when you look at the branching pattern, the drainage pattern that's formed by this canyon at Mount St. Helens, there is a lot of similarities to the branching pattern that we see happening at the Grand Canyon. So at the Grand Canyon, and of course we can't see this today, but there is good evidence of a very large lake system to the east of the Grand Canyon. And the Grand Canyon, given where it's positioned, it cuts through an elevated, what's called an upwarp, a plateau, a high area of the topography in that region. And so the canyon essentially provides the gash that would have allowed water to drain from the east side to the west. And if we superimpose the Little Grand Canyon, we see that it actually has many of the same features, this branching tree-like pattern, these side canyons. What will happen is as the water courses through and cuts in this channel, you'll form eddies that begin to eat away at the sides, and you start to back cut side canyons away from the main channel. We see that at Grand Canyon. We see it at Mount St. Helens as well from the 1982 mud flow. And that basically covers the three significant eruptions from the 1980s. There were others that certainly would have had their part to play. But as far as the highlights that us creationists like to talk about, those are the really important ones. Of course, there have been more recent eruptions. 2004 was the most recent substantial eruption. They actually did evacuate the visitor center, and there was a little bit of a worry for a while, but it settled down, and it seems likely that Mount St. Helens is headed into another period of dormancy for who knows how long. I just discovered this recently. This is a really cool time lapse. I'm just to explain that the red you see on this photo, it's not lava. That's actually, this is a Landsat, and back in the late 70s, early 80s, they colored the healthy forest red. That was just the way they distinguish it. This is a forestry picture, but this is a time lapse that's going to kind of that's going to take us through how the landscape changed or evolved through the 80s as a result of these eruptions. So there's 1980, there's the aftermath of the big eruption, and then subsequent eruptions, of course, continue to add more sediment. In 1982, you really can't tell at this resolution, but watch closely, you'll see that now, after that point, the river shows up again. And I checked this. If you zoom in, there's no river until 1982, and then all of a sudden there's the river again. And that's from when the canyon was cut. And now you can see as the forest and the regrowth begins to happen, and that scar begins to shrink. By the way, if you notice, Spirit Lake looks like it's dancing around a bit. That's the log mat moving around. The lake isn't changing size or anything. That's just the log mat. The last thing to talk about at Mount St. Helens is the recovery, which I just kind of alluded to. We've been talking a lot about the more destructive and constructive, at least if you're a geologist, things that are going on from the eruptions. But what's really amazing to a lot of people, and when they go and they visit the volcano, is how little it actually looks like it just erupted. In fact, what we see at Mount St. Helens is that the landscape and the ecology of the area, the biosystems of different plants and animals that live and work together, that they recover far more quickly than anyone expected they would. Forest succession, the theory about how a forest actually is established in a devastated area, has been completely upended by Mount St. Helens. I read one ecologist in an article or interview where I think she said something to the effect of Mount St. Helens just didn't read our books. The forest came back way ahead of schedule. The animal populations recovered far more quickly than expected. In the aftermath of the eruption, people theorized that Mount St. Helens may have just sterilized itself. We might never see, this might just become, an arid wasteland type of area. Maybe you get some sagebrush or something, right? But in fact, the forest and the wildlife is reclaiming the area very quickly. And there are particular plants and animals that have very special roles to play in how that happens. And we're not going to talk about that now. But again, remember, extraordinary process and extraordinary rate. That's exactly what we see even in the biological recovery in Mount St. Helens. We're seeing that creation is designed in such a way, almost like it was intended to recover devastated landscapes and devastated areas. And of course, if we think about the devastation that would have been left after Noah's flood, that's very interesting because it would have taken some extraordinary pioneering instincts and behaviors to repopulate and reclaim the Earth's surface after the flood. So in summary, the eruptions in the 1980s at Mount St. Helens, it was the most well-observed volcanic eruption in history. I mean, this thing was every second practically was photographed, it was documented, and in the aftermath of the eruption, people have been able to observe every step of the way how the landscape has changed and how organisms and life has responded to it. Again, our theme, extraordinary process, operating, typo there, sorry, at extraordinary rates. The volcanic activity reshaped the landscape and the ecology. It devastated it, and then as it comes back, it's coming back in a different way. The animals and plants, while they're coming back, they're not coming back in the same way that they lived there before. It's not a Northwest old growth forest like it was before 1980. And that's also important to remember. The way that the Earth looks now, the kinds of plants and animals that we have and the places we have them, is not the same as how it was before the flood. We're dealing with an Earth system that was blown away and repopulated. And we know from the fossil record that it didn't repopulate the same way that it was before the flood, because there's a lot of animals that we don't have anymore. And there's entire ecosystems in the fossil record that don't exist today, or if they do exist, they exist in a very different form. And so we see that is also something that is an analogy to the flood. The eruptions challenged assumptions about the processes and rates that were involved in the creation of geologic formations and in the establishment of ecology, of biology, of plants and animals. So for creationists, as a summary, Mount St. Helens is a case study. It's not a one-for-one equivalent to the flood, right? The flood was not a volcanic eruption. It certainly would have involved some volcanoes for sure, but it wasn't an eruption. It was a flood for one thing. It was far more water driven than an eruption like at Mount St. Helens, but it is an example of how high energy catastrophic processes work. And we were able to see it in action and observe it very closely. Mass earth movements, read landslide. That's the first one we saw. They show how the surface of the earth can be reshaped in a matter of moments. And in the aftermath of Mount St. Helens, sorry, we've been able to see that this has happened all over the earth. Mountains have indeed moved. Mountains have been turned upside down. We see slabs of the earth's crust that have been moved thousands of miles, and they've moved very quickly. And so we see that we can't simply take for granted that the solid ground we look at is in fact a permanent feature, and certainly that it wasn't a permanent feature in the past. The tsunami and the rapid transport of logs at Spirit Lake through the mud flows and through the landslide and so forth, they show us that when we see so-called fossil forests, we can't assume that they are in the places where they grew, that they are necessarily representing the forest as in the way that it was when it was alive. Rather, it might in fact have been catastrophically transported and buried there. The behavior of the log mat, the burial of trees, they provide an example of a possible analogy to the formation of petrified trees, of coal, and so forth during the biblical flood. Mud flows demonstrate how sediments can be rapidly deposited and eroded, creating canyons, river drainages very rapidly. And then pyroclastic flows, rapidly depositing thin laminations, thin layers, cross-bedded layers, folded, convoluted layers, showing us that strata can be deposited very quickly in a high energy flow type of an event. And then finally, the rapid recovery of the ecosystem around Mount St. Helens shows us first that creation is very well designed, and it's designed specifically to overcome the challenges posed by devastating events, as well as an analogy to how life could have recovered following the biblical flood. I want to close with a few verses and a few thoughts with this in mind from Psalm 46. God is our refuge and strength, a very present help in trouble. Therefore, we will not fear, even though the earth be removed, and though the mountains be carried into the midst of the sea. When you read Psalm 46 in context, it's talking about not just earth disturbances, but national disturbances, war, and so forth. And the psalmist is declaring his trust and his security, his confidence in God in the face of upheaval and in the face of events and forces that are beyond his control. And that's what we can think about when we think of Mount St. Helens. We're seeing a snapshot of the energy, the power stored in the earth that we have zero control over. We get zero feedback on it. It happens, we get out of the way if we can, but ultimately it's out of our control. And the psalmist is choosing not to be in fear in spite of this. There are forces beyond our control. That is something that humans are terrified of. But this psalmist is saying, we will not fear, though the earth be removed, and though the mountains are carried into the midst of the sea. And then later in the psalm, he goes on and says, come, behold the works of the Lord, who has made desolations in the earth. These forces that seem uncontrollable and that seem like they seem random at times, and yet they're not. They are under the sovereign control, the authority of the God of Scripture, of the God of creation. He has made these desolations, and we are to come and behold them and recognize that he has purposes for these things. Be still and know that I am God. Be still, cease striving, some translations say. Don't fret and don't make yourself anxious over the things that God has not put into your control, things that he is taking the credit for. I am going to work through these forces and through these events. Be still, cease striving, know that I am God. I will be exalted among the nations. I will be exalted in the earth. He will work these things together for his glory. He will work these things together for our good. Our God is an awesome God.